So acids can be classified as strong or weak, depending on the degree of dissociation that they have in solution. So when you have something that dissociates entirely, an acid or a base, you will have a strong acid or a strong base. If it's the acid and the base dissociates just partially, which means that you're going to have molecules mostly in solution, which with just a few ions, you will have a weak acid or a weak base. So we can represent that using an equation. If you have a strong acid like hydrochloric acid in water, you're getting H3O plus Cl minus because the acid is donating the proton to the water molecule, and the water molecule is accepting the proton. So you're getting here your conjugate acid, the conjugate base. And this is just another way of representing the same thing, just without writing down the water molecule. So if you have a strong acid or a strong base, you're going to have 100% dissociation, which means that what you have in solution is only the ions. That's why we use just an arrow pointing towards the product side where you have the ions. Then on the other side here where we have the weak acids or bases with partial dissociation, we're using a double arrow pointing towards the products, your forward reaction, and pointing back towards the reactants, your reverse reaction. That means that you have an actual equilibrium. When you have a weak acid or a weak base, they are described as weak electrolytes. So your acid, for example, in this one, the acid will be partially dissociated to give you H3O plus, the conjugate acid, and the conjugate base. So that partial dissociation means that in solution what you have mostly is your molecule of the acid without dissociating. So usually what we have in solution, it's 5% or less of your molecules are going to be dissociated, giving you the actual ions in solution. So for 5%, you can think about like if you have 100 molecules of this generic acid here, HA, out of the 100 molecules, only 5 of them are going to dissociate to give you the proton and the conjugate base. If you have a strong acid, then what you have in solution, it's only the ions, because if you have 100 molecules of a strong acid, all of your 100 molecules are going to dissociate to give you the ions in solution. Now I have here a list of strong acids. You should memorize them, okay? And then I'm giving you some examples of a weak acid. And there are ways for you to identify like an acid as weak or strong. And this is something that we're going to be looking at later on. So for your strong acids, we have hydrochloric, hydroiodic acid, hydrobromic, perchloric, nitric, and sulfuric. So the first 3 here are binary acids, where you have just the proton with a halogen, in this case Cl, I, and Br. And then the 3 that you have down here, perchloric, nitric, and sulfuric, those are oxyacids. You have a polyatomic ion with a proton, and you have oxygens for all of them. Now, if you look at the first 5 here, for all of them, you have only 1 proton. The last one that I'm listing here, your sulfuric acid, you have H2, which means that that acid contains 2 protons, and both protons are acidic. That acid with 2 protons, it's diprotic. If you have an acid with 3 protons, it will be triprotic. And we call them like polyprotic ions or polyprotic acids, because you have more than 1 proton that can be donated in solution. So down here I have your strong bases, and these ones are easy for you to recognize just by looking at the periodic table. When you have the ion, the polyatomic ion hydroxide, combine with a metal from group 1, and I'm writing just 3, but you can use cesium, francium, which are also in group 1. Those are going to give you strong bases. So you have lithium hydroxide, sodium hydroxide, potassium hydroxide. Metal from group 1, they have a charge of +1. Combined with hydroxide, which is a charge of -1, will give you your formula down here. NaOH, LiOH, KOH. Those are strong bases. There are also strong bases with metals in group 2, but they're going to be strong only at specific concentrations. Now for the weak bases, I have a couple of examples here. We have ammonia, NH3, ammonium hydroxide, which is your polyatomic ion, ammonium with your hydroxide ion, and then we have some compounds containing nitrogen, which are actually derivatives of ammonia. So we have methylamine, this one is missing an L, methylamine, ethylamine, those are also weak bases. And they're derivatives of ammonia because it's replacing one of those hydrogens with something containing carbon. Since they are weak bases, contrary to your strong bases, we have the double arrow representing the dissociation of those in solution. So your NH3, it's a weak base. It's still a base, which means that it's going to accept a proton. So NH3 accepting the proton from the water molecule, and that will give you NH3. It's going to NH4 because it's gaining a proton. And then your water molecule losing a proton will give you the hydroxide ion. So NH3, it's a base. If you look at the Arrhenius definition for a base, it will tell you that a base is a substance that dissociates to give you hydroxide in solution. And that definition cannot be applied to NH3. For sodium hydroxide, that definition can be applied because this one dissociates to give you hydroxide. But NH3, you don't have the ion hydroxide as part of NH3. So NH3, it's a base because actually it gains a proton from the water, and then the water is the one giving you the hydroxide in solution. So NH3, it's a base based on the definition for Bronsted-Lowry. It will accept the proton from the water molecule and you still get the hydroxide in solution, but the hydroxide is actually coming from the water molecule. The water molecule, it's acting as an acid. It's the one that is donating the proton to the base, and the base is accepting the proton. When the water molecule donates the proton, then you get the hydroxide ion, which is going to be the conjugate base in this case because it's coming from the acid. So the acid here is donating the proton, giving you the conjugate base, which is the hydroxide ion. So let's go over conjugate acid, conjugate base a little bit more. So we have the transfer of a proton, right? There's a definition for Bronsted-Lowry. Your proton is being transferred from the acid and the base is accepting that proton. When that happens, you're getting conjugate pairs. Right? So I have here my NH3 molecule and water molecule, it's a H2O. I'm representing that one in a different way because it's easier for us to see the proton and what's happening with the proton. Okay? So I have here my water molecule. I'm representing the water molecule as the positive part right there, bonded to the negative part, which is the hydroxide ion. So NH3 is a weak base. You have it in your list. It will be accepting the proton. The water is donating the proton. So if the water is donating the proton, the water is acting as an acid. So I'm going to write down here my base, which is NH3, and that base, look, your NH3 molecule is neutral. You don't have a charge, which means that the charge is 0. You have the same number of positives and negative charges, so they cancel out. Now, the base is accepting a proton, and your proton has a positive 1 charge. So I'm literally adding NH3 plus H plus. So for your NH3 molecule, you don't have a charge, that's a 0. And now you're adding your proton with a positive charge. So this is like adding 0 plus positive 1, which is going to give you an overall charge of positive 1. Three and 1 here, that will be NH4. And you have your charge of +1. So when the base is accepting a proton, this is what's happening with your NH3. And the product of that combination, base plus proton, is giving the conjugate acid. We can do the same thing here with your water molecule. So your water molecule is acting as the acid. So it's donating the proton. So I'm going to write down my water molecule down here. So remember, your proton has a positive charge, that's +1. And your hydroxide ion, hydroxide, has a charge of -1. So if we subtract or remove H plus from your water molecule, what you're getting now is your hydroxide ion with a charge of -1. So this is the acid losing a proton, because the acid will transfer that proton. When the acid loses the proton, what you're getting right there is a conjugate base. So you have your base and the conjugate acid, and your acid with the conjugate base. And I have here another example. In my second example here, I have my water molecule, and I have a weak acid, which is acetic acid, and the one that I presented before. So you have your acetic acid molecule, which is the one that is going to be donating a proton. And this is the water. Okay? I'm not writing that one in red because now the water is not acting as the acid. The proton is coming from the acid right there. Okay? So your acetic acid is going to be donating the proton, and the water molecule will be accepting the proton, which means that your water molecule in this example, it's acting as the base. So your acid here donating the proton, what you're going to get on the product side is the acetate ion right there. The negative part of your acid, right? Same thing as the previous example here. Water molecule was the acid in this example. It was donating the proton, giving you the negative part of your water molecule, which is the hydroxide. So when your acetic acid donates the proton, what you're getting is the negative part of the acid, which is the acetate ion in this example here. So the negative part of your acid, look, is your conjugate base. In the previous example, the negative part of my acid was the hydroxide, and that's my conjugate base right there. The conjugate base is the product of your acid losing a proton. That will give you the conjugate base, which is the same thing that is happening in this example right here. The acid is losing the proton because that one is being transferred to the base, and you're getting the negative ion, which is the acetate ion right there. So the negative ion of your acid right here is the conjugate base of your acid. And then you have your water molecule, which is acting as a base because it's accepting the proton, and that is giving you this substance here. So HOH is your original water molecule. And now that water molecule is accepting the proton from the acid, and you're getting 1, 2, 3 H's, H3, and your oxygen. And you have a positive charge because your water molecule is neutral. You don't have a charge. And now it's accepting a proton, which is H+. So that proton has a positive 1 charge. And that's why this one will give you a positive 1 charge right there. It's a neutral water molecule accepting a proton. So your acid here, donating the proton, is giving you the conjugate base. And your base here on the reactant side, accepting the proton, is giving you the acid. So I have 2 examples. One where the water molecule is acting as the acid donating the proton, and the second one, this one right here, where the water molecule is acting as a base because it's accepting the proton. So water in 2 different reactions is acting as an acid or as a base. For any substances that can actually do something like that, act as an acid or as a base, they have a special name. They are amphoteric substances, which is the next topic. Amphoteric substances are substances that can actually accept or donate a proton, depending on which substance you have combined with them. So before we move on, let me do something here. And another thing, This is something that you can use to revise your conjugates. Looking at this here, acetic acid, no charge. Your water molecule, no charge. On your product side, you have your conjugate acid, the conjugate base. H3O plus, positive 1. Your acid ion, negative 1. No charge overall on the reactant side. Positive 1 and negative 1, they will cancel out, which means that you have no charge also in total on your product side. So this has to always be true. If this here adds up to 0, on your product side, the charges, they need to add up to 0 too. So let's look at this right here. Water acting as an acid, water acting as a base. Amphoteric, losing or gaining a proton. So when you have an amphoteric substance, if your substance is in the presence, amphoteric substance specifically, if it's in the presence of a base, it will react as an acid. So if you have an amphoteric substance mixed with a base, your amphoteric substance will transfer a proton to the base. If your amphoteric substance is in the presence of an acid, the acid will transfer the proton to your amphoteric substance, which means that your amphoteric substance will be acting as a base. So I have here your two examples, the previous two. The first one, your water molecule was mixed with ammonia, NH3. That one is a weak base, which means that if you have an amphoteric substance like water mixed with a base, your amphoteric substance will be acting as the acid. On the second example, I have my amphoteric substance here, my water, in the presence of a weak acid. The weak acid will be acting as the acid, donating the proton. And now your amphoteric substance will be acting as a base, accepting the proton. So your amphoteric substance can be doing either one, accepting or donating the proton. But it's going to depend on what substance you actually have mixed with them. So I have here my water molecule with a base. So your water molecule, if it's mixed with a base, it will be acting as an acid, donating the proton. To give you here your conjugate acid, the base plus that proton is your conjugate acid. And then here you have the negative part of your acid, which is the hydroxide. That will be the conjugate base. And then I have here my water molecule mixed with an acid, HA. So the acid will be acting as a diacid, and then your amphoteric substance, water in this case, will be acting as a base, accepting the proton. So your base here accepting the proton will become H3O plus in this case, which is your conjugate acid. And then the acid donating the proton will give you the negative part of your acid, which is the conjugate base. Since water can act as an acid or as a base, this here is possible. Autoionization of water means that your water molecule can transfer a proton to another water molecule, and that second water molecule will be accepting the proton. So you have a water molecule acting as the acid and another water molecule acting as a base, donating and accepting the proton. So I'm representing that here, two water molecules. The one that I'm writing down with the H in red is acting as the acid. And then I have a second water molecule acting as a base, accepting the proton. So you have here your water transferring the proton to your second water molecule. This one that is accepting the proton is giving you H3O plus. Your water molecule donating the proton is giving you the hydroxide that you have here, conjugate acid, conjugate base. H3O plus, which we already saw in other examples, is the hydronium ion. OH minus 1, it's something that you already know. It's hydroxide. Now, your hydronium ion is not other thing than a water molecule that has been protonated. You have H2O, and H2O is gaining a proton to give you H3O plus. So that's your hydronium. Since H3O plus is just a water molecule gaining a proton, you will see that these two, we can interchange them. When we're referring to something that is acidic, we're going to be looking at amount of this one in solution, which is the same as the number of water molecules that are being protonated. If you have 100 water molecules and each one is gaining a proton, you're going to get 100 of these ones here. So we can interchange them, and they both represent something, or we look at those amounts to refer to your substances as being acidic or not, depending on how much of this you can get in solution. If you check here, when you have your autoionization of water, we have an equilibrium. Your two water molecules, one acting as the acid, one acting as the base, to give you conjugate acid, conjugate base. It's an equilibrium, which means that we can actually have an equilibrium constant representing that equilibrium. Now remember, like, your equilibrium constant is not going to show any solids or pure liquids. You're going to include in an equilibrium constant anything that is a gas or any ions. Your two water molecules here, they are representing a pure liquid, which is your water. So I'm going to write down L. So we can actually write down our equilibrium constant expression for this autoionization of water here. This K is your equilibrium constant. Since it's for water, we use a W. Equilibrium constant expression, we have always products over reactant. So you have the product of your product concentrations, which means that your product concentrations are multiplied by each other, over the concentrations of your reactants, also multiplied by each other. In this case, we have two products. You have your hydronium and your hydroxide ion. Those are the products, and then on your reactant part, what you have is a pure liquid water, so we don't have to include those in our equilibrium constant expression. So your KW is that hydronium times hydroxide, or concentration of hydronium times concentration of hydroxide. For that equilibrium constant, we have a value equal to and the degree of dissociation is going to depend on temperature. So at room temperature, 298 kelvins, we have 1 times 10 to the minus 14. Now, the autoionization of water is very important for many things, and one of them is explaining the pH concept. pH is a measurement of hydronium concentration in solution, or how much or how many protons you're actually getting in solution. So a pH value will tell you if you have a high or low concentration of that substance in solution. It's the potential for hydrogen. It's a logarithmic scale, which is just the log of the concentration of H3O plus in solution or the concentration of H plus in solution, because they represent the same thing. So I have here two equations that we can use to calculate pH or pOH values. pH value here, the first equation is minus log of the concentration of your hydronium. This is going to tell you like how much hydronium you have in solution based on your pH value here. And that pH and pOH is something that we have in a scale. The second equation that is very similar, it's based on the hydroxide concentration in solution, how basic something is, how acidic something is. H3O plus is what we associate with acidic substances. Hydroxide, it's what we associate with basic substances, the hydroxide part. So this pH scale, it's defined as a scale between 0, and these are just numbers representing pH values, 0 all the way to 14. Okay? The midpoint right there will be a 7, midpoint between 0 and 14. So any pH value that is between 0 and 7 right there represents acidic substances. For a substance to be acidic, look, we're looking at the concentration of hydronium and hydroxide. If the concentration of hydronium is greater than the concentration of hydroxide in solution, you're going to have a pH value that is below 7. And that substance is going to be acidic because you have more hydronium than hydroxide. If you have a pH value that is between 7 and 14, above 7, below or before 14, between this range, you're going to have basic substances. So when a substance is basic, what you have is a concentration of hydroxide greater than the concentration of hydronium. If the concentration of hydronium in solution is going down, it's because the concentration of hydroxide is increasing. They are related to each other. When I wrote down your expression for Kw here, the value of Kw is 1 times 10 to the minus 14. That number is coming from the multiplication of hydronium and hydroxide. So that 1 times 10 to the minus 14 represent these concentrations here for hydronium and hydroxide. Hydronium 1 times 10 to the minus 7, hydroxide 1 times 10 to the minus 7. You have exactly the same concentration because that right there represents a neutral solution. So we can do something here. You have your equation pH if the concentration of hydronium here it's 1 times 10 to the minus 7, we can actually calculate a pH value, because to calculate a pH value, what you need is a concentration of hydronium. So I'm going to put here minus log (1 times 10 to the minus 7), and I get 7. So pH equals to 7 when the concentration of hydronium and hydroxide is exactly the same. So if the concentration of hydronium here it's greater than 1 times 10 to the minus 7, it's because this concentration here is decreasing. This one will increase when this one here is decreasing. For this one here to increase, that one right there needs to go down. So back to the pH scale here. Between 0 and 7, you have acidic. Concentration of hydronium is bigger or greater than the concentration of hydroxide. For basic, you have the opposite. You have the concentration of hydroxide greater than the concentration of hydronium. And then when this here, you have neutral. When the pH is 7, that's what I just calculated. At pH 7, you have hydronium concentration equals to hydroxide concentration. One times 10 to the minus 7, 1 times 10 to the minus 7, pH equals to 7. And one last thing, just useful equations, which are things that I'm going to use later on. So 2 equations that we already saw, logarithmic scale to find out pH or POH values, minus log of hydronium, minus log of hydroxide. Now your pH scale goes from 0 all the way to 14. And you have your acidic values below 7, right? So the higher the concentration of hydronium in solution, the lower the pH. That's what the scale is actually showing you. The higher the concentration of hydroxide, the higher the pH value in your pH scale, because when you have a large concentration of hydroxide, it means that the concentration of hydronium is going down. So things are becoming more basic as you move towards the 14. But it's between 0 and 14. So if you add up your pH value and your POH value, you're going to get 14. The acidic part, the basic part, and the maximum number. This is another equation that we already saw. This is your equilibrium constant expression for the autoionization of water. At 298 or room temperature, that number is 1 times 10 to the minus 14. And these two are not a new equation or anything. This is just rearranging my equations here. This equation, the first one here, is to calculate pH when you know the concentration of hydronium. The second one is to calculate POH when you know concentration of hydroxide. Now these two equations we can rearrange to calculate concentration. So if you know the pH of a solution, you can actually find out how much hydronium you have in that solution. If you know the concentration of hydroxide, you can actually use the same equation to find out the POH of that solution. These two equations here are just rearranging these ones here. So I have minus log, I'm moving that negative sign first on that side. So that will give me minus pH equals log of the hydronium concentration. Then I'm trying to find out hydronium, so I need to get rid of the log. The inverse function of your log here, it's 10 to the, you can check your calculator. Right there, this is my log, and the second function will be 10 to the. So to cancel out the log, to isolate your hydronium concentration, you have to do 10 here to cancel the log, and then 10 on this side, and that will give you 10 to the minus pH because that negative sign is right there. So this one is just rearranging this equation here to get hydronium, and this one here is rearranging this equation here to get hydroxide.